Hi everyone, so today we are finalising and finishing off our last lesson on the normal distribution. So specifically we're looking at the normal approximation to the binomial distribution. So what we have here in these pictures is some graphs produced of the binomial distribution. So this is of the binomial distribution, and we're seeing how that changes due to the values of n and p. So remember, n is our number of trials, and p is the probability of success. So if we have a look at these pictures here, hopefully they make some sense to you. In this first one, we have n is 10, so we've done 10 trials, and the probability of success is 0.2. If I was to work out the expected number of successes here, 10 times 0.2, I would be getting, what is 10 times 0.2? 10 times 2 over 10 is 2. So that's why I'm getting the highest number of successes here at 2. If we're looking at it, we can see that the graph is skewed because we've got a low probability of success. When our probability is 0.5, so half a chance, the graph now looks symmetrical. When our probability is higher, 0.8, then it's again skewed, but in the opposite direction here, because in this case, if I'm doing 10 trials with a probability of success of 8, in this case I'm getting an expected number of 8. So hopefully that makes sense of those shapes. But what we then see is what happens as we increase the values of n. So going down, we're now increasing n. n is increasing as we're moving down here. And what you can see is that regardless of our probability, even if our probability is still 0.2, what you will also notice as n increases is that the graph becomes more and more of the shape of the normal distribution. It is still centered when we have n equals 100, based on this probability, our normal distribution is centered at a different place because we would have a different number for our mean or our expected value. So when I'm working out the mean or the expected value of a binomial, we do n times p. So 100 times 0.2 gives us 20, 100 times 0.5 is 50, or 100 times 0.8 is 80. So our mean is located in a different place. However, regardless, it approaches, the shape begins to look like that characteristic bell-shaped curve of the normal distribution. And you can see how as n increases, the graphs start to look more and more bell-shaped. So because of this, this means that we can sometimes use the normal distribution to approximate a binomial distribution. When do we do this? Generally, it's when we're asked in the question. So you will always be specifically told to use the normal approximation. Don't use it unless they tell you to use the normal approximation. The reasons why they might tell you to use the normal approximation because n is sufficiently large. Now this is obviously quite dubious. Sufficiently large. How large is sufficiently? That's open for interpretation. That's why we wait for the question to tell us to use the normal approximation. In general, however, it's appropriate to use the normal approximation when if I multiply n times p, I get a number greater than 5, and if I multiply n times 1 minus p, the probability of failure, I also get a number of 5. But again, really, you do this when you're told to use the normal approximation. We can work out the mean and standard deviation by using our formulas for binomial. So these are the formulas that we already know that are on the formula sheet, that to work out the mean and standard deviation for a binomial distribution, we have n times p for the mean and n times p times q, or our probability of failure for the variance, take the square root. I think on the formula sheet, this standard deviation isn't given, but the variance is given like this, and we know that the standard deviation is equal to the square root of the variance. So let's look at an example for this. We have a sample of 1,000 people from a certain city were asked to indicate whether or not they were in favour of the construction of a new freeway. It is known that 30% of people are in favour of this new freeway, so that means that P is equal to 0.3. We want to find the approximate probability, so we're using the approximation. We have a sample of 1,000 people, n equals 1,000, and we want to find the approximate probability that between 270 and 330 people were in favour. To start with, we need to work out our mean and standard deviation. So the mean is equal to n times p, so that's 1,000 times 0.3, which will give us 300. And the standard deviation is equal to the square root of the variance, which is n times p times 1 minus p, which is 0.7. I think this gives us the square root of 210, which will give us an approximate decimal. Now, because I'm using the normal approximation, this means I can now define my variable as being normal with a mean of 300 and a variance of 210. But remember, we tend to write it as the standard deviation squared. We're wanting to calculate the probability that x is between 270 and 330. And now we can get our CAS, and whoops, that's not what I want. Sorry, we want to get our CAS. And in here we're using normal because we're using the normal approximation. So continuous normal not PDF, we never use PDF for normal. Continuous normal CDF. Lower is 270. We're going from 270 to 330 with a standard deviation of the square root of 210 and a mean of 300, and we get an answer of 0.9616. So our answer here is 0.9616. Once again, how to know to do this is that we are looking at when the question specifically tells us to use the normal approximation. So that's it for today, and we've now finished off our normal distribution. Congratulations, and as always, let me know if you have any questions whatsoever. Thank you very much.